Moving on to Darcy's Law, we again start off with a little quiz, especially for all those already familiar or slightly familiar with hydrology. Which one of the following sentences presents a correct calculation method? There is only one correct calculation method. A. The hydraulic conductivity is 1 centimeter per day, then groundwater travels 1 meter in 100 days. B. The hydraulic conductivity is 1 centimeter per day and the porosity, which is the maximum volume fraction of water in the subsurface, is 0.4, then groundwater travels 2.5 meters in 100 days. Or is it C? The specific discharge is 1 centimeter per day, then groundwater travels 1 meter in 100 days? Or is it D? The specific discharge is 1 centimeter per day and the porosity is 0.4, then groundwater travels 2.5 meters in 100 days. There is only one right option. Which option presents the correct calculation method? If you like, write down the letter of your choice and check whether it is correct at the end of this lecture. Here we have a cross-section of the subsurface of a flat landscape. We have the land surface, the subsurface is made up of well-sorted sand, we have the water table and groundwater above a water impermeable layer. Installed into the subsurface are two piezometers. Groundwater can only enter the piezometer tubes through the screens at the bottom. Taking the top of the water impermeable layer as a reference level, we see that the water rises to a lower level in the right piezometer. The right piezometer has the lower hydraulic head. Groundwater flows in the direction of the lower hydraulic head, thus from left to right. Can we estimate the velocity of the groundwater flow? If yes, we can also establish the time it takes for a conservative pollutant at the left piezometer screen to reach the right piezometer screen. A conservative pollutant is a pollutant that does not interact with the ground mass, or in other words, the polluting substance goes with the flow. Again, can we estimate the velocity of the groundwater flow? Yes, we can, and for this we can make good use of Darcy's law. In his original experiments, Darcy used a vertical cylinder filled with water-saturated sand. Darcy's experimental setup is represented here in simplified form by a horizontal cylinder filled with water-saturated sand. The experiment starts after the whole system is filled with water. Note that the screens at both sides of the cylinder keep the sand in place, but that water can pass freely through the screens. If the water levels in the two reservoirs differ, then water will flow through the sand-filled cylinder. The water level in the left reservoir is kept at a constant elevation h1 by letting water spill over the edge. Similarly, the water in the right reservoir, which is recharged by the water moving through the cylinder, is kept at a constant elevation h2. If we were to look at this left screen and establish the hydraulic head at, for instance, the midpoint, then this length is the elevation head and this length is the pressure head. Elevation head plus pressure head gives the hydraulic head H1. Actually, everywhere along this screen, whether we are looking here or here, the hydraulic head is the same. So at every elevation along the left screen, the hydraulic head equals H1. Similarly, at every location along the right screen, the hydraulic head equals H2. Water flows in the direction of the lower hydraulic head H2 from left to right through the sand-filled cylinder. Once equilibrium has been established and the water flow has become steady, or another word for this, stationary, the volume flux Q or discharge Q, which is the volume of water that moves through any vertical area A per unit of time in cubic meter per day, can simply be measured by collecting the water that spills over the receiving reservoir during a fixed time interval. Note that the area A is perpendicular to the water flow. Let's do a thought experiment. What would happen if we would enlarge the difference between the hydraulic heads H1 and H2? For this, we could raise the left reservoir to a new fixed higher position, or lower the right reservoir to a new fixed lower position, or do both. Intuitively, you would think that the volume flux, or another word for this, the discharge in cubic meter per day, would increase. So when H minus H2 increases, Q increases. What would happen if we would diminish the distance x2 minus x1? The length of the porous medium resisting the water flow then diminishes, and the discharge would increase. So when x2 minus x1 decreases, Q increases. What would happen if we would enlarge the area A of the cylinder perpendicular to the flow? Then we would also enlarge the area of the pores within this area A through which the water flow actually takes place, and the discharge would increase. So when A increases, Q increases. Importantly, please already know that groundwater flow is through the pores and not through the solid substance, the sand particles here. We can now already establish part of Darcy's law. The volume flux or discharge Q through the porous sand material is linearly related to both the difference in hydraulic heads, H1 minus H2, and the area perpendicular to the groundwater flow, and inversely linearly related to the distance of flow through the porous material, x2 minus x1. Here we have the relation again, but it's not looking very neat, because here I have a term with 1 minus a term with 2, and here it's the other way around. The difference in hydraulic head delta H over the cylinder length is defined as the hydraulic head at the water receiving end, H2, minus the hydraulic head at the water dispatching end, H1, and not the other way around. The distance, delta x, is defined as the location to which water flows, x2, minus the location from where it was dispatched, x1, and not the other way around. For this horizontal water flow, the distance delta x thus equals x2 minus x1. Following these definitions, we can now rewrite the relation as Q being related to H2 minus H1 divided by x2 minus x1, and this times A. But now, of course, with a minus sign added to the equation. The hydraulic gradient is defined as the difference in hydraulic head H2 minus H1 over the porous medium, divided by the distance x2 minus x1 over which this difference in hydraulic head occurs. The hydraulic gradient is given here as a small I, so Q equals minus the hydraulic gradient I times the area A perpendicular to the water flow. Again, regard this area A as a kind of false area, as groundwater flow is not through the area in full, but only through the pore space part of the area, not through the solid part made up by the sand particles. But still, this equation is not looking very neat. To the left of the equal sign, the volume flux or discharge Q is in cubic meter per day. To the right of the equal sign, the hydraulic gradient is in meter per meter, so dimensionless, and the area A is in square meter. So we have cubic meter per day to the left and square meter to the right of the equal sign. And thus we are still missing out on a term in meter per day to the right. This term is the hydraulic conductivity K in meter per day. The hydraulic conductivity is a function of both the properties of the porous medium through which the water flows and the properties of the water itself. Without going into full detail, concerning the properties of the porous material, think of: is it sand, loam, clay, or a mix of these? Is the material well sorted or not? For instance, a well sorted sand will have a much higher hydraulic conductivity than a clay. Concerning the properties of the water, think of its temperature, density, and viscosity. For instance, the hydraulic conductivity increases when the water temperature rises. All these properties of both the porous material and the groundwater itself are captured in this hydraulic conductivity K. Our thought experiment has replaced part of the experiments and observations that led Henri Darcy to his law, which is what we have now deduced. The volume flux or discharge, large Q, equals minus K times I times A. However, if you look in literature, you usually find Darcy's law expressed as small q equals minus K times your hydraulic gradient I. Instead of using small I, the hydraulic gradient for horizontal groundwater flow in literature is also given as delta H over delta X, or sometimes as the differential dH dx. Small q is large Q divided by the area A perpendicular to flow, and thus in meter per day. Small q in meter per day may be mistaken for a velocity, but remember that groundwater flow is only through the pores of area A and not through the area A in full. Therefore, small q, despite its unit of meter per day, is not a velocity. We call small q the volume flux density or specific discharge of the groundwater flow. If we want to know the true velocity of groundwater flowing from x1 to x2, of course, we need to know the porosity, actually the effective porosity. The porosity, usually indicated with small n, is defined as the maximum volume fraction of water in a porous material. The volume fraction is expressed as a number between 0 and 1. As there, for instance, may be stagnating water in dead-end pores in the porous material, the effective porosity N with subscript E is defined as the volume fraction of the porous material that participates in the groundwater flow process. As only the pore space within the area A participates in the groundwater flow, this true velocity, which we call the effective groundwater velocity V with subscript E, must be equal to the volume flux density or specific discharge small q divided by the effective porosity. Also, if we were to inject a coloring dye at the left screen here, we could easily estimate the time it would take for this coloring dye to reach the right screen, simply as the distance x2 minus x1 divided by this effective velocity. Let's return to our problem. Can we determine the velocity of the groundwater flow? Yes, we can, but for this we need some extra data. The subsurface is made up of well-sorted sand. The The hydraulic conductivity will then be in the order of 10 meters per day. We know the difference in hydraulic head to be defined as the lower hydraulic head minus the higher hydraulic head, thus minus 1 meter here. This difference in hydraulic head is established over a distance of 1 kilometer. The hydraulic gradient for this phreatic, or another word for this unconfined water flow, may then be taken as this minus 1 meter divided by 1000 meter, or 0.001. Using Darcy's law, the volume flux density or specific discharge, small q, equals minus k times the hydraulic gradient, minus 10 times minus 0.001 gives 10 to the power minus 2 meter per day, which is 1 centimeter per day. This, of course, is not yet the velocity. To determine the effective velocity, we need to know the effective porosity, Ne, of the well-sorted sand. Ne of a well-sorted sand is in the order of 0.4. The effective velocity, Ve, is small q divided by Ne, which is equal to 2.5 centimeter per day, which is 2.5 meter in 100 days. Answer D of the earlier multiple choice question. For a correct calculation method, you always need to know the porosity, or better, the effective porosity, which was unknown in the earlier multiple choice options A and C. Plus, you need to know the hydraulic gradient, which is incorporated in the specific discharge, but not in the hydraulic conductivity, thereby discarding the earlier multiple choice option B. 2.5 meter in 100 days is 9 meter per year, which is less than 1 kilometer in a century. Actually, the time it takes for a conservative pollutant at the left piezometer to reach the right piezometer is equal to the distance of 1000 meter divided by 2.5 times 10 to the power minus 2 meter per day, which gives 40,000 days, or more than 109 years. And less than 1 kilometer in a century amounts to a mere stretch of 10 kilometers in 1100 years. Thus, groundwater, with some exceptions, for instance in karst areas or when pumped, flows very slowly. And the energy related to the water's velocity, the kinetic energy, therefore did not need to be considered earlier when using Bernoulli's law for groundwater flow. As a side remark, in surface water flow, which is rapid flow and may even be turbulent, evidently the kinetic energy does need to be considered and can then, in a similar fashion as with the other energy terms shown before, be rewritten to a length unit called the velocity head. To finalize, as take-home messages, we have observed that unconfined groundwater can flow along curved pathways. We know that groundwater flows in the direction of a lower total energy, a lower hydraulic head, and thirdly, as just deduced, groundwater generally flows very slowly. Also, the minus sign in Darcy's law, as well as the differences between specific discharge, being a volume flux density, and the hydraulic conductivity and the effective velocity, all in units of meter per day, have been explained. This lecture introduced groundwater hydrology, so there's much more. Very important in mastering hydrology is to struggle with exercises. I wish you success with all your future hydrological endeavors.